So quickly, okay, very simple problem. So the idea is that the way, for example, there is this one thing which is a big rage now, that ask students to learn from their neighbors predominantly, like especially during tutorials when they are allowed to interact, mainly because whatever doubts they have, okay, are the doubts which we may not be able to anticipate. But whereas like they can share each other's concerns in a much better way. But that aside, what we will quickly go through is what do we emphasize the students that the way we are going to solve this problem. First we draw the free body diagram, okay. Clearly as we had discussed earlier, we see that this is a fixed support. Now one of the errors that many students do is they forget that this is a fixed support and they will take that as a hinge. And because of that, what happens is that they will have only Ex and Ey and they will not have this moment which is necessary for this fixed support. Now what happens is that we are specified what is the tension in the cable. So if the tension in the cable is not specified, then the current problem, the way it is given, has 3 unknowns here and 1 extra unknown, plus 3 plus 1, 4 unknowns. So this becomes a statically indeterminate problem. But we are given what the tension in the cable is. So with these 3 reactions, okay, this becomes a statically determinate problem. On the other hand, we take this cable tension to be 150 kilonewton and keep this as a hinge. Then we have only 2 unknowns and 3 equations, and you will see that the system, okay, will not be a stable system. There will be multiple solutions for the system, which in other words mean that the system is not in equilibrium. Okay, so this is the most important point, that the free body diagram has this moment. And once we have that, okay, one way to do is, for example, we emphasize the students that what are the mistakes that they can make. Okay, so this is, if you write an equation like this, sigma fx equal to 0, if we say that this is Ex plus cos 36.9 into 150 kilonewton, okay, so which is this angle? Okay, so this is not taking an appropriate equation for equilibrium, whereas what we do is that we know that all these distances are given to us. This is 4.5, 6, and the hypotenuse will be 7.5. So 4.5 by 7.5 is the sine of this angle, which will be the horizontal component, okay. And if we do 6 by 7.5, so one of the mistakes students make is, look, that this angle is 150 kilonewton. So strictly speaking, for equilibrium in the horizontal direction, we want 4.5 divided by 7. But many times students say it is 6 divided by 7.5. So what we have to emphasize, so one small trick to emphasize here is that if this cable were perfectly straight, which means that the vertical distance is very small and horizontal distance is very large, then essentially this value becomes 1. In the other extreme, when the vertical distance is very large compared to the horizontal distance, then this value becomes 0. So essentially what matters for finding out the component in the x direction for this cable is this distance 4.5. So this is very common mistake. The students will write 6 divided by 7.5, and that is not appropriate. And we have to again see that the signs that we have chosen, that this is Ex, which is plus. So if we take the component of Fx, that will also has the same direction as Ex. So that also should be positive, whereas many times students make mistake with this, the plus they will make as negative. So those are the points that we want to emphasize. And when we emphasize that, like, all these equations are perfectly fine. This cos, why was it wrong? Because if we take this theta, 4.5 by 7.5, okay, will be sine inverse of 36.5. Okay, so if you do cos, then they are taking the vertical components. So these are the common mistakes that the students make, which we want to make sure, okay, we want to emphasize that these are the common mistakes that you students can make, and we want to make sure that they know what is happening. And again, as I had discussed earlier, that we tell them that what is the negative sign signify. It just means that we have to repeatedly tell them that Ex ka direction we assumed it to the right, but it is really to the left. Is that what we have to emphasize? Now the idea is that if the students has taken this as the hinge support, then they are gone because this ME is not there. But truly speaking, okay, for this system to be in equilibrium, okay, we have to first, now if you want to find out, what is the equilibrium in the y direction, okay, so these are the two appropriate choices, and the same mistakes which student had done earlier, that the vertical now what are the components, we are taking Fy, y as positive, so Ey is positive, this is fine, okay, but if you take minus 44 into 2, 20 kilonewton, that is also great, okay, But if you do plus 6 by 7.5, 6 by 7.5 into 150 is perfectly right, the vertical component, but then that should be minus because it is pointing downwards. So students make these mistakes quite often. So with all these things in mind, okay, so this will be the right equation, EY in the vertical direction, minus 4 into 20 in the downward direction, so minus cos 36.9, this angle is 36.9, you can verify on the calculator, okay, or it is equal to 6 divided by 7.5, you can write, and that into 150 is fine, or if you write 6 by 7.5 with a minus sign, because this is acting downwards and our y is taken to be positive, then this is the right equation of equilibrium. Okay. Again the same thing about positive and negative sign. Okay. And another thing is that we make them discuss with their neighbors so that they know, okay, what mistakes they are making, because very likely the neighbor and the student would be likely to face the same problem. So it's a good idea, but again that's a optional thing. The main thing is to emphasize them that what are the appropriate conventions that they should be choosing. Now ultimately we want to take torque about E, and when we take torque or moment about E, whatever, okay, torque, moment are equivalent things, we can use whatever we like. Then the components are what? So it is this 20 into 18 into 1.8 into 4, that is 7.2. How will it act? It will act in the anti-clockwise direction. Plus 20 into 5.4 plus 20 into 3.6 plus for the last force 20 into 1.8. Okay. So these are all the torques of these 20 kilonewton forces about this. And then finally, what do we want? Now this is one very interesting point, that this force can be resolved into two components. One is a vertical component, one is a horizontal component. Now the horizontal component, mind well, okay, horizontal component passes through E, so that will have no contribution to moment about E, whereas the vertical force has a moment arm of 4.5, and what direction the torque will be? It will be in the clockwise direction, and that's why we take a negative sign here, because the sign convention that we have chosen is anti-clockwise is positive, so that is a negative sign. Now note one thing, somebody has asked previously the principle of transmissibility. Now this 4, instead of breaking it here, you can say that the 4, so this tension 150 kilonewton force is acting at point D, and now when you break it there, you will have a horizontal component and a vertical component. Now the vertical component passes through point E, and that will not have any contribution. So the only contribution will be now this horizontal force into 6, and you substitute all the values, you will see that this 4.5 will come here and this 6 will go there. So whatever you get the moment about point E, you can either resolve the force here or resolve the force here, you will get the same answer. So that is one another point, which is like another demonstration of principle of transmissibility that you can emphasize to the students. Okay, so this is the brief discussion. Okay, if you want to add or point out anything, we can have a 2 minutes brief discussion and then move on to the next problem.
1139.
If constraints are more than 2, 3, 4, 5, 6 like that, and if those are passing through single point.
Yes, so that's the point. So for example, you are totally right. Okay, it's a very good point that you are making. Yes, so I can do a very simple example like this. So for example, I have rollers like this, okay, coming like this, okay. Then I have another roller which is acting like this, okay. These are all perpendicular. Then I have a third roller, okay, which is acting like this, and I may have more of them, this, and I may have huge number of such constraints, okay, like this. And that's what I think you have in mind. And if I draw the free body diagram, I am not removing the roller right now for just saving time. The reactions will look like this, like this, like this, like this, like this. Okay, so we have 5 reactions. So naively, if we think that 5 reactions, it's a statically indeterminate structure, then we are wrong, as you rightly pointed out. So having 5 reactions doesn't mean that your structure is stable. But as we had pointed out briefly, that even if I have 5 reactions, they all meet at a point. Now to this structure, if I apply a force like this, then the structure will be unstable. Why? Because there is nothing to balance the moment that this force has about this point O. So as you rightly pointed out, just having more constraints doesn't mean that the structure is stable. But what happens is that if you have more constraints and the structure is properly constrained, then it becomes statically indeterminate. Like for example, in our problem, we have this, and this is 150. But in this problem, additionally, now this is a stable system clearly, okay, this is a very stable system, but additionally if I also put a roller like this, then the number of unknowns becomes 3 here plus 1 reaction here, and so this is a 1 degree of statically indeterminate structure, okay, it has 1 degree of indeterminacy. Okay, I think that answers your question hopefully. Okay, so we can move on now, okay. We will move on to the next problem now. There is one thing I just wanted to emphasize is that when we did moment equilibrium, we could have chosen any point we want to. We could have chosen A, B, F or some any point in Timbuktu. But the reason we chose E for the simple fact is that these two unknown forces to begin with, which were unknown to begin with but which we found out by calculation, they do not contribute to the moment about point E for this free body diagram. Okay. Now what you can do is that there can be a check that you can use, that if you gotten some answers, are those answers right or not, what we can do, we can use these values and then take torque about say point F for the entire set of forces acting on this free body diagram, and then if our answers are right, then that torque should also come out to be 0. So that is a consistency check that we can use. Okay. So we will now move on to the next problem. Let us move to the third one, which is a little bit simpler. Okay. And this problem is there for a reason. I want to emphasize one point. It's a very simple problem otherwise, but there is one point that I want to emphasize. So which I will emphasize at the end in the discussion. Okay. So what we have is that we have a simple rod A, B, C, D. This rod, okay, is supported by 2 sleeve supports. Okay. These are 2 sleeve supports which are small sleeves supported on these rigid rods and connected by pin to the main rod ABCD. And on the top we have a string, okay, which is connected at point A, and at the other point it is connected to a fixed support, and the angle it makes with the horizontal alpha is equal to 30 degrees. To this rod we are applying a force of 150 Newton, and what we want to know is the tension in the wire and reaction at B and C. Now this is a sleeve support, and if you remember what we had done is that if you just take this sleeve independently, okay, if the sleeve is completely free, okay, not connected to anything, then this sleeve is free to slide like this. Because it is connected by pin to this rod, okay, the rotation of this rod with respect to the sleeve is also free, and the sleeve is a small sleeve, okay. So there cannot be any reaction that the sleeve provides in this direction. There cannot be any torque that this short sleeve can provide at this point. Only reaction that the sleeve can provide is that the sleeve is incapable of having any motion, any possible motion in the direction perpendicular to the direction of these rods, and so that will be the reaction that will act. Okay. Now we are asked to find out that for this system what is the tension in the wire and the reaction at B and C. So there is a method which is much more quicker, and there is a method which is not that difficult but which takes solving simultaneous equations. Okay. So we will again get back to this problem in less than 10 minutes when I will briefly discuss this, and we will move on to another problem. Okay, so we are back. Okay, a quick problem. It's a very straightforward problem. The free body diagram will look like this. Okay, the free body diagram looks like this at point C. Okay, just note what was this angle. This angle was 30 degrees. So the reaction will be perpendicular to this. Okay, like this. At point C, this angle is 30. Reaction will be perpendicular to this for the reason we had discussed. Okay, this tension, the tension will act along this direction, and so this will be the free body diagram. The simplest way to solve this diagram is this problem is to just assume a horizontal x axis and a vertical y axis, and you can take moments about the points, okay, and sum of all the forces. But what will happen is that no matter what you do, you will end up getting 2 simultaneous or 3 simultaneous equations. You will never get an equation where there is only one variable that is present, only one unknown variable present, and P. But instead what we do is that, and this is a trick which we can keep playing again and again for certain problems. What we ask ourselves is this: what happens if this string were not present? Now if this string were not present, what will happen is that this rod, okay, will try to slide in this direction. Okay, so it will try to slide in this direction. Why? Because the 2 support reactions that are acting are in what direction? Perpendicular to this here and perpendicular to this. Okay, so any force, okay, this P has a component which has any force which has a component, okay, this P has a component which is perpendicular to this, okay, these support reactions won't be able to balance them. So that is our trick to understand that what is the appropriate coordinate system to use. So what we do is that we define a coordinate system x which is parallel to this line 60 degrees and y which is perpendicular to this. What we had just seen is that in the absence of the tension provided by this wire, this rod has two reactions and this P component will have a component which is perpendicular to these two reactions, which is P cos 60, and these will not balance them. So then what we do is that we just take equilibrium along this inclined y direction, and a component, if you can see from geometry, is that T cos 60 will be balanced, will balance the component of the force P cos 60 perpendicular to the wire, and you balance them and you will immediately see that T is equal to P. And once you get that, then it's straightforward. What you do is that for this free body diagram, we already know what T is, then take torque about point B, you will immediately see that you will find what is the only FC, T and P will not contribute, only T and FC will contribute. Just do the moment balance, you will see that FC is equal to minus 150 root 3, which means that the direction is opposite to what we had chosen. Similarly, to find out what is the reaction at B, we take torque about point C. What do we get? Simple moment balance, which we had discussed for ample number of times. You will see that FB is equal to 300 root 3, which is acting in the direction that we have chosen. So the simple point is that you can solve this problem by using x-axis as the horizontal and y-axis as the vertical. But using geometric intuition, what we realize is that these two support reactions are parallel to each other, and this applied force has a component that is perpendicular to these two parallel reactions, and it is this tension which is balancing that, that particular contribution. And so it is advantageous for us to use a coordinate system which is inclined like this, and the advantage is that instead of getting simultaneous equations with more than one unknowns in any equation, all our equations have exactly one unknown, and because they have exactly one unknown, they are easier to solve, and as a result the students will be less prone to making errors. That is the only point of this question. Okay, so we can take one quick question and then we will move on to next problem, which is a little bit more involved.
1307, do you have a question?
Sir, if you are considering a horizontal beam as per the sample problem that you have given there,
which problem?
Have, the loading and reactions, you have the sample problem there, sir.
Okay.
And the beam was horizontal, and there was a hinge support, there was a roller support also. So at the hinge support, hello, sir, at the hinge support, we have two types of, you have given the two components of the reactions only there. But at that particular place, since the beam is horizontal and all the loadings were vertical,
yes,
so only one reaction is there to be there.
Okay.
Horizontal reaction will not be there. We do not have to take sigma
no,
is equal to
but
0.
I see your point. Okay, so this is a very common question which even students, like for example, you raised a very good point which is important to answer, because if you take a beam like this, there is a reason why we do that. Okay, there is a reason, there is a proper bookkeeping. So we have a roller like this, and you have a very valid point that since there is a roller and I don't have any horizontal force, I only have a vertical force. So when I draw the free body diagram, why shouldn't I just draw this? AY and BY. Why can't I just do that? Why should this be included? Why? This is A and this is B. And the reason is that it is simple bookkeeping. If you have already the proper intuition, you may as well say that this AX is equal to 0. But what happens is that then when you do that, you should not use then the only two equations that are left to you, then instead of 3 you are left with only 2 equations. Okay, so if you can do that properly, that when you remove this AX, you are implicitly using the equation sigma fx equal to 0, and there is a chance that you may forget that afterwards, and like the students may get puzzled and say, oh, that this is already 0 and we should have 3 equations, but that third equation, where has it gone? So you have implicitly used that, and for that confusion to not be there and to have appropriate bookkeeping, what we say is that there is a possibility of Ax, and let me then use equilibrium in the x direction and then convince myself that that is equal to 0, rather than jumping the gun and immediately saying that it is equal to 0, because there may be some very subtle cases. Okay, now this is horizontal rod, there may be some other subtle cases in which it may not be immediately clear that there should not be any horizontal reaction. So it is just a decent practice to keep that Ax and then later on say that my equilibrium equation in the horizontal direction makes it to be equal to 0. Okay, so we will now move on to the next problem. Okay, so this was a very simple problem. That was one point that I wanted to make. The appropriate choice of coordinate axis can greatly simplify the problem. That there is no hard and fast rule that we always should have x in the horizontal direction and y in the vertical direction. By appropriately choosing the direction of x and y, we can greatly simplify our problem, and that was essentially the point of this question. A simple question it was, but this point is what we wanted to emphasize and what we want to tell the students, that there is nothing sacred about horizontal and vertical for x and y. Choose what x and y is appropriate for that problem, so that the problem becomes as simple as possible and as less prone to error as possible, and in line with our physical intuition. Okay, so we now move on to this problem. Okay, it's a reasonably interesting problem. Okay, it's a very interesting problem, very simple, but there is some amount of geometrical thinking that is involved in this problem. So the only small trick in this problem, okay, so what we have here is we have a rod which is connected by two strings AC, BC, both actual length is 4 meter, and length of AB is 4 meter, AB ka length is 6 meter. Now what we are doing is that we want to hoist this beam up by attaching a string, pulling it over a pulley and applied a load P. Now hoisting means that when the beam is lying on the supports, then there will be some reactions that are provided, and when we want to hoist it, these reactions will become 0. The only trick is that when you lift this up, what you realize is that the simplest error that students do is that they assume that when the beam goes up, AB remains horizontal. Now that is not possible for the simple reason is that ACB, when you lift it up, will form a proper equilateral triangle, and the line joining from C, where the force P acts on it, so this will have a tension of P, and when this have a tension of P, the line of action of P passes through a distance of 2 meters from support A. But the weight of the beam acts at a distance of 3 meter from this support A. As a result, this P and this W are not in the straight line, and that will result in torque, and that will end up rotating the beam like this. So the idea is that the beam will rotate by how much amount, it is still an unknown, that unknown is theta, but how much will it rotate by? It will rotate by an amount such that the load P acting at point C, and this distance is always, it will act in such a way that the center of gravity of the beam through which the load passes will be directly below this. So that is essentially the concept, that the rotation should be such that this load P ka direction, the line of action of load P should pass over the center of gravity of AC. And then this is the final geometry of the problems. The unknowns are TA, TB and this angle theta. Now what do we do is this, that these two are unknown. So first we should know that this beam should be at equilibrium in the horizontal direction. So TA cos this angle is 60 minus theta, what A makes with the horizontal, because this is theta. So the angle that TA makes with the horizontal is 60 minus theta. For B, angle that TB makes with the horizontal is 60 plus theta. And for equilibrium in the horizontal direction, this is the condition, TA cos 60 minus theta, TB cos 60 plus theta. Now for this beam, we can take moment balance about point B. So we will get one simple equation like this, only involving TA and W. Second equilibrium equation will be TB will have an equation like this. Now the unknowns present here are theta, TA, TB. So 3 equations, 3 unknowns. What we can do is that from these 2 equations, we will immediately see that TB equal to 3 TA, and then use the first equation, you will get an equation like this, which you can very easily solve to find out that theta should be cos inverse of 12 by 13, and just substitute in one of these equations, you will see that TA equal to W by root 13 and TB is equal to 3W by root 13. So the only trick present in this problem is that AB cannot remain horizontal, because if AB remains horizontal, the line of action of P does not pass through the line of action of W, and as a result there will be a net torque on the beam and the beam cannot stay in equilibrium. So it has to come to equilibrium in some inclined position like this, and the inclination of the beam is also another problem in this beam. So 3 equations, 3 unknowns, and our consistency, mathematical consistency is taken care of here. So if you have any queries, we will have some discussions for 2-3 more minutes before moving on to the next problem.
1192, go ahead, we can hear you.
I have a question on equilibrium of body, sir.
Okay, please.
As we have seen, when the different forces, acting on the body nullify each other, the body remains in equilibrium.
Okay, that is only one part, because all the forces and the moments both should like be nullified. Sum of all the moments acting on a free body and the sum of all the moments, external and the moments created by force, both should nullify only and only then the body is in equilibrium.
Yes.
Not just the forces, also the moments.
Yes. Yes, sir. Forces and moments, when they are nullified, the body remains in equilibrium. Now my question is, when Earth is a rotating body, now it's rotating about its own axis. Now how we will explain the equilibrium of such type of body like Earth?
Oh yeah, so those, like, you know what, these are the problems which we should not worry about with this. These are the points about, they are called as moving reference frame systems. And typically, strictly speaking, okay, so there is like, our Earth is a non-inertial frame of reference. So strictly speaking, we should not be talking about all this equilibrium business and so on. But what we assume is that for our daily purposes, okay, that the rotation speed is so small, okay, that like for example, for all practical purposes, okay, for all our equilibrium on our Earth, those Coriolis forces and the other forces, okay, so that is beyond the scope of this course, okay, that we neglect those forces, okay, totally we neglect those forces. But if you really write down equations of equilibrium properly, all those forces that come from the rotation of the Earth should also be taken into account, okay, and we will see that we are strictly speaking not in equilibrium, because we are rotating and any rotation would involve like lot of forces, centripetal forces, Coriolis forces and whatnot, okay, so that is beyond the scope of this course. Here we are assuming that we are in some kind of a local shell in which the rotation effects, for example, and they are not that dominant. They are important, but for all the practical purposes, all the other forces that are involved, this particular force is much smaller compared to the other forces that are involved, so we neglect it. But you have a very valid point, but that is beyond the scope of this course. Okay, so Earth is a non-inertial frame of reference, okay, we are already in deep waters there.
1253.
The doubt is that in case we have 4 unknowns,
okay,
and three equations, how to solve analytically such kind of problems?
Okay, pray to God, okay, because 4 equations, 3 unknowns, okay, you cannot solve it, and these are called as examples of statically indeterminate systems. I am not saying that you cannot do anything about it. For example, in tomorrow's tutorial you will see that there are certain statically indeterminate problems where the number of equations is actually less than the number of unknowns, but the geometry of the problem is such that you can obtain certain forces, but clearly when the number of equations, okay, is less than the number of unknowns, you cannot obtain all the unknowns, okay, that is the general theorem in linear algebra. So either you have no solution or you may have multiple solution, okay, so it depends on what the equations are. But typically speaking, you will not have a unique solution, and these kind of problems typically come under the purview of structural mechanics, strength of material, where you use what are called as compatibility conditions, and then you attempt and get extra equations from displacement criteria using principle of virtual work and so on, and then solve those problems. But as far as EMEC is concerned, we are not using those techniques. So within EMEC, if you get 4 unknowns and 3 equations, by and large, okay, the train stops there. Okay, so we are done with this problem. So the one question which was asked about Earth being rotating and a non-inertial frame of reference is a very interesting question. Only thing is that the forces that come from those non-inertial rotation of the Earth and so on, they are typically much smaller compared to the weight of the body or other forces that are involved, and so we don't need to bother with them as far as our general engineering problems are concerned. But there are certain applications which are so sensitive, for which you need to take into account all those forces and the kind of problems and the kind of values you need to input, or the kind of the sensitivity you need in that analysis is far more. But whereas in our course we are looking at a very simple set of problems where the problem themselves may be kind of non-trivial, but all these subtle issues coming from the rotation of the Earth or our revolution around the Sun, those things, okay, are much smaller compared to the other forces involved, and the kind of sensitivity we want in our calculations. So moving on to the next problem, okay, so there are many other problems. So 3-4 more problems are there. Okay, so you can solve them at your leisure, okay, when you go back. But there is one simple problem that we are trying to understand is a uniform 400 kg drum. So you have a uniform drum, okay, a uniform 400 kg drum is mounted on a line of rollers. So we have a line of rollers, okay, so the drum is like a cylinder and there is a line of rollers. What is a line? So this is the plane through which I am looking. So the line of rollers is coming out of plane. So there is a line of rollers at A and there is a line of rollers at B. Now what is asked is that a 80 kg man moves slowly a distance of 700 millimeters. Okay, the geometry is given to you that the man's center of gravity lies at a distance of 700 millimeters from point O. And all the rollers are perfectly free to rotate. Now this is the crux of the problem, that at A, all the rollers are perfectly free to rotate. What does that mean? If they are all perfectly free to rotate, then they cannot have any lateral friction. They can only exert a normal load at point A. Whereas at B, all the rollers are free to rotate, means all the rollers at B are also free to rotate, which means that they can exert only a normal reaction except one, okay, which must overcome appreciable friction in its bearing. What is a bearing? That the roller is it's like a pulley and it is connected to the support by some bearing, and there is a lot of friction between that roller and the bearing. What does that mean? That the force that one particular roller that will exert on this drum will have one horizontal component and one vertical component, okay, and which must overcome appreciable friction in its bearing. So it has capacity of producing, because it is not free to rotate now, it has a capacity of producing both a horizontal force as well as a vertical force. Now with this in mind, what we are asked is that calculate the friction force exerted by that one roller tangent to the drum, okay, that what is that tangential force that is exerting on this drum, as well as the magnitude R, okay, of exerted by all the rollers at A on this drum for this condition, okay. So A, all the rollers can exert only a normal reaction here. B, all the rollers can exert except one, which can also exert a tangential force in addition to normal force. So we want to know what is the total normal force by all the rollers on the drum and what is the friction force that one stuck roller is exerting on this drum at point B, given this is the configuration of the person and the drum. Okay, so I think many of us got the answer. Okay, it's a reasonably straightforward problem, but the reason I decided to discuss this problem, that even though it is not too difficult, the only thing is that we have to ensure that there are two free bodies here. Okay, so strictly speaking, it is not a one body problem, that this person, okay, inside, that is another free body diagram. So what we want to know is what is the reaction that this person exerts, okay, at this point. Now note that if you draw the free body diagram for that person, there may be whatever reactions coming from the contact of this person with the cylinder, but the weight acts downward 80 kgs, and for the equilibrium of this person itself, no matter what it does, okay, the total reaction can only be vertical and in line with this 80 Newton. As a result, this 700 meter where the center of gravity of the person is present, okay, should itself be the line at which the effective reaction that the person exerts on the cylinder. Because we draw the free body diagram and realize that whatever is the weight of the person, equal and opposite and along the same line should be the reaction of the cylinder on this person, and then by Newton's third law, this 80 should act on the cylinder, and this is our free body diagram for the cylinder. And then afterwards it is straightforward that what is going to happen, that if we take this cylinder, these normal reactions pass about the center. Now the weight of the cylinder is supposed to be, the cylinder which is supposed to be homogeneous also passes through point O, and as a result, now what happens is that this force F, okay, is the only way in which the torque that the reaction created by the 80 kg of the person can be balanced. If there were no F, then all these three other forces pass through O, and the torque that the person exerts on the cylinder, there is no way to balance that. So it is that stuck roller here which is providing this friction F that is balancing this, and in straightforward we take torque for this free body diagram about point O, we get that W into 700 minus F into 800 should 1800 equal to 0, we get immediately F. And to find out what is the reaction of all the set of rollers at point A, we can do one thing, we can take for this free body diagram what are some of all the torques of all the loads about point B, and then we can immediately obtain what is RA. Or another thing, note that this is 60 degrees 30, so RA is perpendicular to RB. So we already found out F. What we can do is that we can take equilibrium, force equilibrium in the inclined direction, and what you will see is that you do whatever way, you will get the same answer, and that's a cross check that you can have at your disposal. Problem 5 is also a little bit of a challenging problem. Okay, so let me quickly discuss this problem, okay, before we retire for the day. It is a little bit different than whatever we have discussed till now. So what we have is that, again, we have a semicircular rod, okay, ABCD, which is supported by frictionless rollers, okay, at point B and at point C, and there is another roller support at point D. So what does this mean is that this support B can exert a reaction only in a direction perpendicular but only outwards. So the direction of the reaction exerted B on this rod can only be towards O, and the direction of the reaction that is exerted at point C can only be towards O. It cannot exert a reaction which is in the away from O. Because why? Because there is not a contact here. It is, for example, it is situated, it is placed on this roller, so it can only press against it but cannot lose contact with it. And now what we are asked is that for this system, you are applying a load P at some angle theta, and you are asked to find out what is the maximum theta that is allowed at this point, okay, such that this system remains in equilibrium. Okay, so that is the point. Okay, but what we can do is that before that we can have a 2-minute discussion session on the previous problem.
Any question from 1, 2, 3, 5? We can hear you. Go ahead.
Sir, my doubt is about joint, sir.
Okay, which joint? What problem?
Sir, in a pasted joint, how can you take this, sir?
Which
For example,
sorry?
cricket bat with handle. The handle is pasted with the bat, sir, right, sir?
Yes.
So how can we consider that joint, sir? Is it a hinged or a...
It has to be a fixed joint, because if it is not a fixed joint, it is a hinge joint, then the handle can rotate about the bat, right? The main body of the bat. So it has to be a fixed joint if you want to just model it like a simple EMAC problem. There will be distributed forces acting at the contact point. So if you draw a free body diagram for a handle, this is the main part of the meat of the bat, and this is the handle. So if you draw the free body diagram only for the handle, okay, and there are forces acting on this handle, then in that case there will be a lot of distributed forces, friction and other things between the handle and the main part of the bat. But effectively, if you look at statically equivalent system, this will look like this. Okay, there will be a lot of distributed forces, but the effect of that, as far as the dynamics of rigid body is concerned, or equilibrium of rigid bodies is concerned, is this will be equivalent to 3 forces and a torque like this. Okay.
Sir, I am having another doubt, sir. So, is there any difference between normal bearing and lengthy bearing, sir? So I have met with a problem. Actually, by considering the normal bearing, we are taking that as a simply supported.
Okay, which? By
considering lengthy bearing, we are taking that as a fixed support. Is it right, sir?
So I can understand what, but it's a, you are right, I agree with you. Okay, so for example, you can have a sleeve like this, a big sleeve, okay, and you can have a beam like this. Right, you are saying like this, right? And this is fixed like this. So you are totally right. If, for example, this sleeve is relatively large, then what happens is that you are restricting the rotation of this beam as far as this joint is concerned. And if you draw the free body diagram of this, what will happen is that this point will connect here, this point will connect here, and if this sleeve is reasonably large, then these 2 forces can create a torque, and the equivalent system then has to be written like this. This reaction may not be there depending on if there is a friction or not. So it will be something like this. So you are totally right. If the sleeve is large, then what can happen is that this point of the beam can contact here, this point can contact here, and that combination may lead to a equivalent torque. And so when we draw the free body diagram, we may have to replace that with a torque like this. I agree with you.
Okay, sir. Thank you, sir.
Yeah, thanks. So in this problem, the concept is as simple as possible, is as simple as this, that at support B, the reaction can only act inwards, at support C, the reaction can act only inwards. Okay. So what we decide is that our load acting at an angle can be broken into two parts, Py and Px. So let us analyze these two problems separately to figure out what may be the issue that can creep in, that why do we need a restriction on the angle. What we see here is that what we emphasize the students is that since the reaction can only act inwards, so let us look at this problem. So you can immediately figure out by taking moment about point O that f dy should be 0 here. Now this Fb will be a combination of Fb1 and Fb2, where Fb1 comes from applying a load horizontally and Fb2 comes from applying load vertically, same for the reaction at C. Now, the note here is that when a horizontal load is applied, this reaction can immediately be figured out to be 0 by taking torque about point O, and then what you will figure out by this, by taking torque about point C, that Fb1 is equal to minus Px. So Fb1 is not inwards, okay, but it has to be outwards. But that is not possible. This support B will not allow you to exert a reaction on this in the outward direction. It can only exert a reaction like this, because otherwise when this is negative, this rod will lose contact with the support. But now what happens is that if you apply a load P in the vertical direction, Py, then you will see that the reaction at this point, okay, Fb2 is positive and given by 2 root Py by 3, whereas here it is negative and given by minus Px. You can convince, we can convince ourselves that the reaction at C is always positive. So what is happening is that this load in the horizontal direction is trying to make this rod disrupt equilibrium about point B, whereas the vertical load is only stabilizing, and the combination is Fb is equal to Fb1 plus Fb2, which now has to be positive for this thing to be in equilibrium, because if this becomes negative, it means that the rod is going to lose contact at support B. And for this to be greater than 0, this is the condition that we get. Px can be written as P sin theta, Py can be written as P cos theta, and this greater than or equal to 0 will give us a condition that tan theta should be less than 2 by root 3, which is approximately 49 degrees. So that is the crux of the problem, that you apply horizontal load, this support tends to get disrupted, vertical load, the support is stabilized. When you apply combination, the combination can be such that the total force at Fb should be positive inwards, and if you increase the angle, you will see that this becomes dominant and the support and the rod will lose equilibrium at contact B. Okay.